If we're talking about extrema of a function, we're really talking about minimums and maximums. And as we focus on these things, there's two different kinds, in a sense. There are absolute minimums and maximums. And absolute minimums and maximums are the highest or lowest y values. Right? The absolute maximum of a function is the highest y value you could have. The lowest, or the absolute minimum of a function is the lowest y value you can have. Right? So if we were to look at just a simple graph, that's a parabola. Right? The vertex of this parabola represents its absolute minimum. Right? It cannot get any less as an output. And in the same way, another parabola looking something like this point is the absolute maximum. Right? There's nothing higher than that vertex. We also have, though, what are called local or relative minimums and maximums. And these are on intervals, but they could be the absolute maximums as well, but not necessarily. For example, again, just considering a quick graph of something. Here's a graph. It's probably a quartic. This graph has, starting from the left, this is a local maximum, right? Because it represents a high point, but it's not the highest point. This point here is a local minimum because it represents, say, a low point, but it's not the lowest point. And this value up here is the absolute maximum. Right? The highest output occurs there. And this particular graph does not have an absolute minimum because as this function continues on, as x goes to infinity or negative infinity, it just keeps decreasing in value. So that would be an example of these. Now, for absolute extrema, so again, absolute minimums and maximums, these occur at the critical points. And the critical points for absolute maximums are the endpoints on a closed interval right, so let's say we're focusing only from -3 to 3. Well, then the endpoints would be -3 and 3. Right, so the critical points are the endpoints, and they're also where the derivative equals 0. Anytime we're looking for extremes, for minimums and maximums, we must always look at the endpoints and where the derivative equals 0. Right, those are the things that matter. Local mins and maxes do occur at the same places. It just doesn't make as much, but absolute extremes is where we need to focus. So anytime we're looking for mins and maxes, we need to look at all of the critical points and evaluate them. What's going on at the endpoints, what's going on when the derivative equals 0. That's where we're focusing. So for example, we were to look at the function f of x equals 3x to the fourth plus 4x cubed minus 12x squared plus 10. And the question is, what are the critical points? Well, this is on an open interval, right? We're not telling you that we're focusing on a certain set in the domain, so there are no endpoints to look at. So the critical points occur whenever the derivative equals 0. And the derivative in this case is 12x cubed plus 12x squared minus 24x. And this derivative will factor, which is nice. I can pull a 12x out and be left with x squared plus x minus 2. And that will factor even further into 12x times x plus 2 times x minus 1. And this means that the zeros for the derivative will occur at x equals 0, x equals negative 2, and x equals positive 1. Right? These are the three critical points. Now the question could follow, which of these, where do minimums and maximums occur? What we can do to evaluate this is use what's called sign analysis to decide what's happening. And here's the principle behind what's happening here. So let's say we had graphed this. And if you graph this, our graph looks something like this. Now it's fourth degree, so we know that it's going to be doing something like this. And we can see graphically that looks like there's a local minimum here, whatever this x value is. Looks like there's a local maximum here, whatever that x value is, and another local minimum here. Now you can't always see the graph, and we can't appeal to the graph, but we're going to consider our reasons here. Notice that the tangent lines to the right of this point are going down, right? That means their slope is negative. It becomes 0 at whatever this point is, and then the tangent lines change to positive, right? So the slopes of the tangents go from negative to positive at this local minimum. Then at this local maximum, the tangent lines, their slopes are positive. Here at the point, they would be 0, and then the tangent lines change and have a slope that's negative. So at the local maximum, the lines change, the tangent lines, their slopes change from positive to negative. And again, at the third point, where there's a local minimum, the tangent lines are going down, their slope is negative, it goes to 0, changes to positive and increasing. So again, at the minimum, the slopes change from negative to positive. Our sign analysis will replicate that same idea. What's going on with the value of the derivative before negative 2, between negative 2 and 0, between 0 and 1, and after 1? And the way we do this is I'm just going to pick a value, like negative 3, and I'm going to plug it into the derivative. And all I'm interested in is what is the sign of the derivative's value at negative 3. And what I can see is that 12 times negative 3 will be a negative number. Negative 3 plus 2 will be a negative number, so the product of the first two things will be positive. Negative 3 minus 1 is negative, so I have a positive times a negative number. So before negative 2, the value of the derivative will be negative. Next, I'll test negative 1. Right? What's going on between negative 2 and 0? And I'll do the same thing. When I plug negative 1 into the first part, 12 times negative 1 will be negative. Negative 1 plus 2 will be positive, so the product of the first two numbers will be negative. Negative 1 times minus 1 is negative 2, which means the product of everything will be positive. So the value of the derivative between negative and 0 will be positive. Repeat again using 1/2, right? Between 0 and 1, what's happening? When I run through that, this first term is positive, the second term is positive, the third term is negative, their product will be negative. After 1, if I check 2, the first term is positive, the second term is positive, the third term is positive, their product will be positive, and I can see that since my derivative changes from negative to positive at negative 2, there must be a local minimum. Since it changes from positive to negative at 0, there must be a local maximum. Since it changes from negative to positive at 1, there must be a local minimum. Right? In terms of expressing my answer to the question, are there local minimums and maximums? There are local minimums at x equals negative 2 and x equals 1 because f prime of x changes from negative to positive. There's a local max at x equals 0 because f prime of x changes from positive to negative, right? And this language is important. Sign analysis, this right here, is useful to help you interpret what's going on, but it alone is not a sufficient answer. These descriptions are what are necessary anytime you're explaining your reasoning.